Hi, here's some feedback on your work on the stability of the distributed ring of benzene. The work was generally done to a very high degree of quality. The only questions that I need to supplement the mark scheme with are 2 B and C. Right, so everybody did 3 times 1 bond for 2A. And B and C, here's the mark scheme. Let me just bring up the mark scheme for you. Everybody pretty much got the marks for these, although I did detect some just learning by rote and writing it down. Okay, in particular the explanation as to what stability means. Right, so it's the marks as in this mark scheme are all you need to know for A level. And you can remember the responses to these questions if you like, but they sort of depend on a little bit of acceptance of what stability is and why the distributed ring is more stable. So I think it would help if I just explained a little bit more in depth what stability means in this context and what makes the distributed ring more stable. So in the mark scheme we had a simplified enthalpy diagram, and I think what we'll do is to explain this is just to draw a more detailed enthalpy diagram. Right, so on the y-axis, let's draw a nice big enthalpy axis here. And one of the things to appreciate is that chemical potential energy, or enthalpy, is in this context sort of like the opposite of stability. So when the word stability is being used in this context, it's sort of the opposite of enthalpy or chemical potential energy. So that's supposed to be an L there. So let's draw a little diagram, a little sort of green axis there that is the opposite of enthalpy. So if a molecule has got high enthalpy, it has a lot of where is that enthalpy? It's in the bonds, right? And that means it's unstable, high enthalpy, unstable. And that means it doesn't require a lot of energy to break. Okay, so as usual on our x-axis, that's like progress of reaction, isn't it? Progress of reaction from reactants to products. And let's just separate this into 2 halves. And on the left-hand side, we can do the distributed model. And on the right-hand side, we'll do an enthalpy diagram of the Kekulé model. Okay, so let's do distributed. Let's do the final product is cyclohexane in both cases, isn't it? All right, and the final product is cyclohexane. So let's just draw that out like so. And so you've got the same in both cases. We're ending up with the same final product, cyclohexane, right? And they are the same enthalpy, same chemical potential energy, same stability. Okay, but in the case of the distributed model, we're saying that it's less exothermic to hydrogenate, right? So let's draw our distributed model like so. And as we know, that experiment suggests that it is exothermic, but only minus 208 kilojoules per mole. Whereas when we look at the Kekulé model and do our predictions, it's more exothermic, which means we need to start our Kekulé model up here somewhere. Right, so if we start our Kekulé model up here, then it's more exothermic, right? And that's minus 360 is what we would predict if we started with a Kekulé model. And that's all consistent with the mark scheme so far. But what the mark scheme doesn't delve into is the fact that the enthalpy change of the reaction is, of course, the sum of bond breaking and bond making. All right, so that's why I want to draw this diagram. So the bond breaking process is going to result in the same intermediary in both cases. All right, so let's draw our intermediary up here, and we're going to draw the same thing up here. So the intermediary is when our benzene molecule has got 3 broken pi bonds. So 3 broken pi bonds, let's just, there's an unpaired electron on each of the carbons. All right, so as you can appreciate, very reactive. And also we'll need to break the bonds in our 3 hydrogen molecules, right? So we're going to have 6 hydrogen radicals as well. So let's draw them like that. Okay, and it's the same in both cases, right? So we'll draw the same thing out here. We've got 3 broken pi bonds, right? So we'll represent that intermediary that's by 6 unpaired electrons on each of the carbons, right? And 6 hydrogen radicals as well. So that's exactly the same. So what we're saying is that, let's draw this in red, this energy endothermic process, right, to break the bonds in benzene is more endothermic than the same process as in our theoretical Kekulé model of benzene. Okay, so it's more exothermic. More endothermic to break those bonds, right? Because it starts off lower down the enthalpy axis because of the fact that the electrons in the pi rings are sort of distributed and therefore less densely negatively concentrated. Okay, but the exothermic process, the bond forming process, is the same, right? We're starting off with our same intermediaries, and we're finishing off with our same final product, which is cyclohexane. Right, so the exothermic process, this is the endothermic process, this is our exothermic process. So we just draw this. So you can see in both diagrams, the exothermic process is the same, but the bond breaking for the distributed model is more endothermic because there's less densely negative charge in the distributed ring. So hopefully that explains the concept of stability and why the distributed model is described as more stable.